This video will contain 4 problems. They are the 4 that I handed out in class on Friday. So if you've solved these, you can skip this video. But if not, pay attention. A mass of 10 kilograms is falling to the earth. When it is 10 meters above the ground, its velocity is 5 meters per second. What is its mechanical energy just before it hits the ground? Key to understanding this is mechanical energy, which of course is made up of potential energy plus kinetic energy. That number is the same everywhere for a given object, assuming there is no friction. If there's no friction, if you figure out the mechanical energy 10 meters off the ground or anywhere else, you will know it everywhere else, including right before it hits the ground. So all we have to do is figure out its mechanical energy just before it hits the ground, or right at 10 meters. So let's see what we know. Potential energy is made up of ma sub g h, and kinetic energy is made up of 1/2 mv squared. So now we'll just throw in the numbers. For potential, it's 10 kilograms was its mass, acceleration to gravity 10 meters per second squared, and its height 10 meters. And then we'll do the same thing for kinetic energy. It said when it was 10 meters up, its velocity was 5 meters per second. So 1/2 mass times velocity squared. We crank the problem out for that. That's 1,000 joules worth of potential energy and 125 joules worth of kinetic energy. And when you add those up together, it becomes 1125. That is the mechanical energy when it's 10 foot high off the ground. But if there is no friction, that is also its mechanical energy everywhere else, including right before it hits the ground, so you don't have to do any other work. That right there is the solution that we were looking for. Let's look at another one. The handles of your lawnmower make a 35-degree angle with the ground. If you exert a force of 25 newtons while doing 300 joules of work, how much distance did you cover? Well, you remember the definition for work is a force that causes a displacement. A force times the amount of displacement times the cosine of some angle. That angle is the angle between the force and the displacement it causes. This blue line is supposed to represent the displacement that your lawnmower experiences. The red line is the downward force that you are exerting on it. The angle between them, of course you're exerting the force up in the air, but in any case, the angle between them is this number. So, and all of those were given to us in the problem. We have to solve for delta D because that's what we were asked for, how much distance. And let's see, that would be work is force divided by cosine of theta. I plug the numbers in that I know, 300 joules for work, 25 newtons for force, cosine of 35 degrees. Grab my calculator, and that comes out to 14.69 meters. That's how far you went doing 300 joules of work at 35-degree angle and 25 newtons worth of force. That's all there is to that one. In this problem, we are given a slide. The problem says that it's frictionless. I did not bother to write down the words, but I gave you the picture there. The top of the slide is 1.5 meters off the ground, right here. Bottom of the slide is 0.25 meters off the ground, right there. At the top, it has no velocity, so the problem told us. And it's asking for its velocity down here. It also told us its mass of 15 kilograms. Well, since it said there was no friction, then mechanical energy is going to be conserved. That is, we'll figure out what it is at the top, because we know everything we need to know to figure that out, and it'll be the same number down here at the bottom. So, as always, mechanical energy is kinetic, which can be potential energy plus kinetic energy. And that takes the form with gravity of, for potential, mass times the acceleration due to gravity times the height above the ground, plus kinetic, 1/2 mv squared. Well, let's see what we know about those. We know everything we need to know for potential. 15 kilograms worth of mass, 10 meters per second squared for the acceleration due to gravity. Now the height, I have said that the height is 1.5 above the ground. There's a different way to do this. I'll tell you about it in a moment. Well, let's go ahead and solve this one this way. And then we do the same thing for kinetic energy. 1/2 the mass times the velocity squared, but at the top, of course, the velocity is 0. So the second term works out to 0. That makes the total there 225 joules for potential plus 0 joules for kinetic for a total of 225. Okay, let's look at it down at the bottom. At the bottom, what do we know? Well, still, mechanical energy is potential plus kinetic energy. And that's potential still m a sub g h, and kinetic still 1/2 mv squared. But now we know that the mechanical energy is 225 joules, because that's what it was up here at the top. So 225 joules is equal to the potential. Now this is the mass, the acceleration due to gravity, and 0.25. That's how high it is off the ground, 0.25 here. So that's the potential. And then the kinetic, 1/2 the mass times v squared. We do not know what v is. That's what we're trying to figure out. And now it's a matter of simplifying the terms, and you grab your calculator and you solve for v. You will find out that v works out to exactly 5 meters per second. But there's another way of looking at this. We are never really interested in the absolute amount of potential energy. We're just interested in the relative amount. That is, remember the animation with the dog riding the skateboard where we move the little blue line which set the potential energy 0 point? Well, let's say we decided that we were going to say, since during our problem the box only falls to the bottom of the slide, let's make that the point where we're measuring potential energy from. That would mean this term right here, it's not 1.5 meters that it can fall, it's 1.25. That would be the 1.5 off the ground minus the 0.25 that it doesn't fall, or that the slides above the ground, I guess, is 1.25 meters, which would change this term to 18.75 joules. So we have to change here to 187.5. But over here, the height now is 0. I put 0 in here, this first term goes away, and when I solve 187.5 is equal to 1/2 15 times v squared, I still get 5 meters per second squared, because it does not matter where we define 0 on our potential energy. Let's do one more on this. This one says, if a force of 27 newtons causes an object to move 17 meters in 11 seconds, how much power was required? Well, power is just the rate at which you do work. Total work divided by total time taken. So we'll have to calculate the work. Let's do that first. Work is force times the displacement caused by the force times the cosine of the angle between the two. And we were given in the problem everything we needed. 27 newtons worth of force, 17 meters worth of displacement. And it does not say they're at any angle, so we can assume they're moving at the same angle. The displacement and the force are at the same angle. So that'd be cosine of 0, which works out to 1. And when you crank that math out, it's 459 joules. And as I said a moment ago, power is merely work divided by time, how long it took you to do the work, or the rate, rather, at which you did the work. And we plug in the numbers, 459 joules divided by the 11 seconds offered by the problem. Work that out, it comes out to 41.7 watts. And watts is the unit for joules per second. And of course, you could break joules down into kilogram meters and seconds also. And that's it, both for this fourth problem and this video.